Hello students, welcome to this lecture on sequences and series. We would be learning the Abel's test and Dirichlet test um, for the convergence of an arbitrary series. So let's start discussing Abel's test and Dirichlet test. First of all, we will be discussing a lemma that is called Abel's lemma. So Abel's lemma says that if Sn is a sequence, if Sn is a sequence of partial sums, okay, if Sn is the sequence of partial sums of the series summation An, all right, such that the uh, the nth partial sum Sn lies between small m and capital N for all n, alright, and if Bn is a sequence of non-negative, Bn is a sequence of non-increasing and non-negative real numbers, that means Bn, you can say that Bn is a sequence of decreasing and decreasing sequence of positive real numbers, then this summation AK Bk, k varies from 1 to n, lies between small mb1 to capital MB1. If yes, all right, if the nth partial sum of the series An lies between small m and capital N, then and Bn is a sequence of decreasing positive numbers, then the summation AK Bk, k varies from 1 to n, lies between small mb1 to capital MB1. This is called Abel's lemma. We will prove it. So the proof goes like this. We know that Sn is the nth partial sum of of the series An. So Sn is A1 plus A2 plus A3 plus An. That means S1 is A1, S2 is A1 plus A2, S3 is A1 plus A2 plus A3, alright, and so A1 is S1 and A2 would be S2 minus A1, but A1 is S1, so A2 is S2 minus S1 and A3 would be S3 minus S2, alright, and similarly SAN would be SN minus 1 and so on. Now this summation AK BK k varies from 1 to n, which this is A1 B1 plus A2 B2 plus AN BN. This can be written as A1 is A1 is S1 S1 into B1 plus A2 is S2 minus B2 S2 minus S1 into B2 plus AN is SN minus 1 into BN. Alright, so this is equal to S1 into B1 minus B2. Okay, S1 is common. Take S1 common. B1 minus B2 plus S2 is B2 minus B3 plus S3 is B3 minus B4 and so on. And in the end, you have Sn minus 1 is Bn minus 1 minus Bn and plus Sn Bn. Alright, so this is summation AKBK. So let's call it 1. Alright, uh, now what we have got is summation AKBK is S1 into B1 minus B2 plus S2 into B2 minus B3 plus Sn minus 1 into Bn minus 1 minus Bn plus Sn Bn. This implies this summation AKBK k varies from 1 to n is greater than or equal to m into B1 minus B2 plus m into B2 minus B3 plus m into Bn minus 1 minus Bn plus m into Bn. Why? Because every Sn lies between small m and capital M. Okay, every Sn lies between small m and capital M. So every Sn is greater than or equal to small m. That is why. So this can be written as m1 into b1 minus b2 plus b2 minus b3 and so on up to bn minus 1 minus bn plus bn. All right. So all these terms cancel with each other, minus b2 plus with b2 minus b3. All right. So what remains is m1 b1. Everything else would cancel out. So we have got that summation ak bk k varies from 1 to n is greater than or equal to m b1. Let's call it 2. Also, this summation AKBK n varies from 1 to n, which is S1 into B1 minus B2 plus S2 into B2 minus B3 plus Sn minus 1 into Bn minus 1 plus Sn into Bn. This implies this summation AKBK n varies from 1 to n is less than or equal to capital N into B1 minus B2 plus capital M into B2 minus B3 plus capital M, right, into Bn minus 1 minus Bn plus capital M into Bn. Alright. Why? Because Sn is less than or equal to capital M for all n. Because Sn is less than or equal to capital M for all n. So this alright, as earlier, as in 2, this is equal to capital M B1. So we have got that from 2 and 3 we have got that summation AK Bk, alright, k varies from 1 to n, lies between MB1 from 2 and from 3 it is less than or equal to MB1. Alright, and that is what we wanted to prove. So we have completely proved this lemma that is called Abel's lemma, which says that if Sn is the sequence of partial sums of a series summation an, and if Sn is bounded by small m and capital M, and if Bn is a decreasing sequence of positive terms, then summation AKBK k varies from 1 to n lies between MB1 and capital M B1. So this is what we have proved. Next, we are going to prove the Abel's test. Using Abel's lemma, we would be proving Abel's test. Alright, so Abel's test says that if the series summation A and Bn is a convergent series, if the series summation A and Bn is a convergent series and Bn is a monotonic and bounded sequence, and Bn is a monotonic and bounded sequence, then the series summation A and Bn n varies from 1 to infinity is also convergent. Okay, if the series summation An is convergent and Bn is a monotonic and bounded. Monotonic means either monotonically increasing or monotonically decreasing. Bounded sequence, then the series A and Bn is also convergent. So how do we prove this Abel's test? The sequence Bn is monotonic and bounded. Okay, this is given to us. The sequence Bn is monotonic and bounded. Hence, by monotone convergence theorem, the sequence Bn is convergent to its LUB. Okay, if you have a monotonic, uh, if you have a monotonic sequence, every bounded monotonic sequence is convergent. Okay, every bounded monotonic sequence is convergent. So since Bn is monotonic and bounded, so by monotone convergence theorem, Bn is convergent to some number B. Okay, let's define a let's define Un like this. So Bn is convergent to some number B. Let's define Un like this. Un is B minus Bn. If Bn is a, if Bn is an increasing sequence. Okay, if Bn is increasing sequence, then we define Un to be B minus Bn. And if Bn is decreasing sequence, then we define uh, Un to be Bn minus B. So Un is B minus Bn if Bn is increasing, and Un is Bn minus B if B is decreasing. Now we discuss two cases. Case 1 is if Bn is increasing. If Bn is increasing sequence. In that case, Un is defined to be B minus Bn. So if Bn is increasing and also Bn converges to B. So Bn is monotonically increasing and Bn converges to B. So B has to be the least upper bound of the sequence Bn. Okay. If Bn is monotonically increasing and Bn converges to B, then B has to be the least upper bound of Bn. And B is the least upper bound of Bn means Bn is less than or equal to B for all n. And Bn is less than or equal to B for all n implies B minus Bn is greater than or equal to 0 for all n. And that is what U1 in the case Bn, in the case when Bn is increasing, Un is B minus Bn. So that means Un is greater than or equal to 0 for all n. In the case 1, when Bn is increasing, Un is greater than or equal to 0 for all n. Alright. And Un minus Un plus 1 is, okay, this is how Un is defined, B minus Bn, in the case when Bn is increasing. So it is B minus Bn minus B minus Bn plus 1, which is nothing but Bn plus 1 minus Bn. And since Bn is increasing, so Bn plus 1 is greater than or equal to Bn. And that means Un is greater than or equal to Un plus 1 for all n. And that means Un is a decreasing sequence. Alright. So Un is a Un plus 1 is less than or equal to Un means Un is a non-increasing. Okay, we should write non-increasing here. All right. So Un is a non-increasing. Un is decreasing, no, Un is non-increasing, all right. Un is non-increasing, or you can say Un is decreasing. Yes, all right. Un plus 1 is less than or equal to Un. So Un is uh, decreasing, all right, not increasing but decreasing. So Un is decreasing sequence of non-negative terms, right? Non-negative because of this, right? So Un is a decreasing sequence of non-negative numbers. Is this clear? So next, case 2, when Bn is decreasing. So case 1 was when Bn is case 1 was when Bn is right increasing, when Bn is monotonically increasing. The next case is when Bn is monotonically decreasing. So when Bn is monotonically decreasing, all right, uh, then and also Bn converges to B. So if Bn is monotonically decreasing and Bn converges to B, then B is has to be the GLB of Bn, greatest lower bound of Bn. If Bn is monotonically decreasing and Bn converges to B, then the limit has to be the greatest lower bound of Bn. So that means Bn should be greater than or equal to B for all n, because B is the GLB, and that means Bn minus B is greater than or equal to 0. And in the case when Bn is decreasing, in that case we define Un to be, in the case when Bn is decreasing, we define Un to be Bn minus B. Okay, so all right. Uh, So, un, which is bn minus b, would also will be greater than or equal to 0 for all n. So, un is a sequence of positive terms, and also un minus un plus 1 in this case, all right, would be this number bn minus bn plus 1, and since bn is monotonically decreasing, so bn minus bn plus 1 is greater than or equal to 0, and that means un is greater than or equal to un plus 1, and then hence again un is a monotonically decreasing sequence of positive terms or non-negative numbers. So whether you have case 1, all right, whether you have case 1 or case 2, in both the cases un is a, all right, decreasing sequence of non-negative numbers. Whether you have case 1 or you have case 2, okay, whether you have case 1 or you have case 2, in both these cases all right, in both these cases un is a decreasing sequence of non-negative numbers. So now un is this b minus bn, in if bn is increasing, and bn minus b if bn is decreasing. So bn can be written as un minus b, bn can be written as b minus un if bn is increasing, and b plus un if bn is decreasing. So summation a and bn would be sorry, then so a and bn would be a and b minus a and un if bn is increasing, and b a n minus a and un if bn is decreasing. Now since this series is convergent, summation an is convergent, therefore summation ban is also convergent. Now we shall now show that summation an un, this series, is also convergent. This series summation an un is convergent. This is what we will show now. All right. So that we will do on the next page. So now since an is convergent, so by Cauchy's general principle of convergence, okay, since an is convergent, so by Cauchy's general principle of convergence, given any real number epsilon positive, there exists natural number n such that am plus 1 plus am plus 2 plus an is less than epsilon for all n greater than or equal to m. This is Cauchy's general principle of convergence. So since an is convergent, so by Cauchy's general principle of convergence, this happens. Now using Abel's lemma, Okay, using Abel's lemma, am plus 1, um plus 1 plus am plus 2 plus um plus 2 plus an un would be less than um plus 1, and un plus 1 is less than u1 because un is monotonically decreasing sequence of positive terms. So using Abel's lemma, since un is a decreasing sequence of uh, uh, positive terms. So using Abel's lemma, we have got this result, and that means by Cauchy's general principle of convergence, the series summation a n un is convergent. Also, BAN, this series is convergent, we already know. So summation AN BN is convergent because AN BN is BAN minus AN UN if BN is increasing, and it is BAN plus AN UN if BN is decreasing. So the series summation AN n varies from 1 to infinity is convergent. Okay, that completes the proof of Abel's test. So we have proved Abel's test. And Abel test says that if a series is convergent and Bn is a monotonic and bounded sequence, then the series summation a and bn n varies from 1 to infinity is also convergent. Okay, this was Abel's test, and we have proved this completely. Okay, now we are going to do the next test, that is called Dirichlet test. Okay, what does Dirichlet test says? Dirichlet test says that if the series an is a has bounded partial sums, if the series an has bounded partial sums and the sequence bn is a monotonic sequence such that bn converges to 0, right? If the series an is if the series an has bounded partial sums and bn is a monotonic sequence which converges to 0, then the series summation a and bn n varies from 1 to infinity is also convergent. Okay, so this is a Dirichlet test. If a series has bounded partial sums and you have a monotonic sequence which converges to 0, then the series summation a and bn is also convergent. This is Dirichlet test. How do we prove this? So replacing bn by minus bn if needed, replacing bn by minus bn, we can assume that the sequence bn is monotonically decreasing. Because if bn is monotonically increasing, then the sequence minus bn would be monotonically decreasing. If bn is monotonically increasing, then minus bn would be monotonically decreasing. So in any case, we can assume that bn is monotonically decreasing and also bn converges to 0. So we are assuming that bn is monotonically decreasing and converges to 0. So bn is converging to 0 from the right hand side. Okay, on the real line, bn is converging to 0 from the right hand side. So let Sn be equal to a1 plus a2 plus a3. Okay, nth partial sum of the given series. Since it is given that the given series has bounded partial sums, so the sequence Sn is a bounded sequence. So the sequence Sn is a bounded sequence, and that means there exists a real number capital M, so that mod of Sn is less than or equal to m for all n. Alright? This happens because it is given to us that the series summation n has bounded partial sums. Now, for n greater than n, we have am plus 1 plus am plus 2 plus am plus an, which is equal to Sn minus Sm. This is less than or equal to mod of Sn plus mod of Sm, and mod of Sn and mod of Sm are both less than or equal to capital M. So it is less than or equal to 2m. All right. Uh, so we have for n greater than or equal to m, am plus 1 plus am plus 2 plus an is less than or equal to 2m. Also, it is given to us that bn converges to 0. Since bn converges to 0, so given any real number epsilon positive, since bn converges to 0, so given any real number epsilon positive, there exists a natural number m1 such that Bn is less than epsilon by 2m for all n greater than or equal to m1. Alright, why this happens? Because Bn converges to 0. Since Bn converges to 0, so given any real number epsilon positive, there exists a natural number m1, so that Bn is less than epsilon by 2m for all n greater than or equal to m1. Alright, and hence by Abel's lemma, for n greater than n and for m greater than or equal to m1, am um plus 1 bm into bm plus 1 am plus 2 bm plus 2, all right, this modulus is less than, all right, 2m, hmm, 2m into bm plus 1. This is by using Abel's lemma. And bm and bn is less than epsilon by 2m for all n greater than equal to m, so it is less than epsilon by 2m into 2m, and that is only epsilon, all right. And hence we have shown, okay, hence by Cauchy's general principle of convergence, the series summation a and bn is convergent, all right. Is this clear? So we are so if a series Bn is has bounded partial sums and Bn is monotonic sequences that Bn converges to 0, then the series Bn A and Bn is also convergent, right? And I hope this is all clear to you. So next we would be discussing some exercises, right? So uh, first of all, we will review what the test that we have done. First test that we have proved is Abel's test. This test says if the series summation a and bn is convergent and the sequence bn is monotonic and bounded, then the series a and bn is also convergent. This was the Abel's test. And the next test that we have done is called Dirichlet test. All right, Dirichlet test says that if a and bn has bounded partial sums, okay, and bn is a monotonic sequence such that bn converges to 0, then the series a and bn is convergent. So in the Abel's test, the series an is a convergent series and the sequence is monotonic and bounded, all right, then the series summation a and bn is convergent. But in the Dirichlet test, the series, we do not require the series to be convergent, we just require that the series has bounded partial sums. So this condition that the series an is convergent has been relaxed to say that the series an has bounded partial sums. And we have made the second condition stronger. In the Abel test, we were requiring this sequence Bn to be monotonic and bounded sequence. In the Dirichlet test, we are saying that Bn must be a monotonic sequence, but it must converge to 0. Bn must converge to 0. Alright. Then the result is same, that the series An is convergent. All right. So this is the difference between Abel's test and Dirichlet test. So you have a look at them carefully, and now we will do some exercises based on Abel's test and Dirichlet test. So the first exercise that we do is this: test the convergence of the series 1 minus 1 over 3 into 2 square plus 1 over 5 3 square minus 1 over 7 4 square, and so on. All right. So we have to test the convergence of this series. So let a n be equal to minus 1 raised to power n minus 1 over n square, and let bn be equal to 1 over 2n minus 1. Alright, then this series can be written as summation an bn, n varies from 1 to infinity. So if you take an to be minus 1 raised to power n minus 1 over n square and bn to be 1 over 2n minus 1, then the given series can be written as summation an bn, n varies from 1 to infinity. Now the series an, all right, the series an is the series minus 1 is n minus 1 over n square as n varies from 1 to infinity. All right, if you take the absolute values of an, this is simply 1 over n square, so it will, so the series of absolute values, all right, is simply summation 1 over n square, which is convergent by p test. And since so, and that means the series an is an converges absolutely. Alright, that means the series an converges absolutely. And if a series converges absolutely, then the series itself is convergent. So the series an is convergent because it converges absolutely. Also, bn is a monotonic sequence because bn is 1 over 2n minus 1. So it is monotonically decreasing sequence of positive terms. Alright. And so it is since it is monotonically decreasing sequence of positive terms, and it also converges to zero, so it is bounded. All right. So Bn is monotonic and bounded. All right. All terms of Bn lies between 0 and 1. So hence by Abel's test, the series summation A and Bn would be convergent by using Abel's test. All right. So I hope you have understood this exercise. So we have done exercise 1. Exercise 2 says show that the series summation minus 1 raised to n minus 1 over n, 1 plus 1 over n, 1 plus 1 over n raised to minus n is convergent. Okay, how do we show that? Let a n be equal to minus 1 raised to n minus 1 over n, and bn be equal to 1 plus 1 over n raised to minus n. Alright, then the given series can be written as summation a n bn, n varies from 1 to infinity. Now this series summation a n varies from 1 to minus 1 raised to n over n is convergent because of Leibniz test. Because of Leibniz test, this series is convergent. And what about bn? Bn, if you take the limit of Bn as n tends to infinity, this limit is 1 over e. So the sequence Bn is convergent, and since it is convergent, so it is bounded. So Bn is monotonically decreasing. This is how you can show that Bn is monotonically decreasing. 1 plus 1 over n, alright, Bn is less than Bn plus 1. You can show by by expansion using binomial theorem. You can show that Bn is monotonically decreasing. Alright. So by Abel's test, the series summation A and Bn would be convergent. Alright. By by Abel's test, the series summation A and Bn would be convergent. Is this clear? We will do before we do the next exercise. We have to do this these two formulae. First formula is that sine alpha plus beta plus sine alpha plus 2 beta plus sine alpha plus n minus 1 into beta is equal to sine of alpha plus n minus 1 by 2 beta multiplied by sine n beta by 2 divided by sine beta. And if you have cos alpha plus beta plus cos alpha plus 2 beta plus cos alpha plus n minus 1 beta, then it can be written as cos alpha plus n minus 1 by 2 beta into the rest of the things is same, sin n beta by 2 and sin beta by 2 as in the first formula. So these two formulae we must be knowing before we do the next exercise. Alright. So the next exercise is test the convergence of summation nx over n raised to power p, where n varies from 1 to infinity. That's the convergence of summation nx over n raised to p as n varies from 1 to infinity. So let an be equal to cos nx and bn be equal to 1 over n raised to p. Alright. Then the given series can be written as summation a and bn, n varies from 1 to infinity. Alright. Let Sn be the nth partial sum of the series an. Then Sn would be cos x plus cos 2x plus cos 3x plus cos 4x plus cos nx. And by using the formula that we have just done, this would be equal to cos of x plus n by 2 into x into sine nx by 2 divided by sine x by 2. Alright. So that can be written as sine n plus 1 by 2 n plus 1 by 2 x sine nx by 2 divided by sine x by 2. Alright. Now if you take the absolute values of s and x, alright, this is less than or equal to 1 over sine x by 2, because in the numerator both the terms are less than or equal to 1. So mod of sine x is less than or equal to 1 over mod of sine x by 2 can be written as cosecant of x by 2. So sine x is a bounded sequence for all those values of x for which uh, sine x by 2 is non-zero. So the sequence the sequence Sn is bounded by cosecant of x by 2 for all those values of x for which sine of x by 2 is not 0, and sine x by 2 is not 0 means x is not a multiple of 2 pi, integral multiple of 2 pi. So the sequence Sn is bounded for all those values of x, all right, uh, for which x is not an integral multiple of 2 pi, because for those, if x is integral multiple of 2 pi, then sine x by 2 would be 0. So uh, now What about Bn? Bn is 1 over n raised per p where p is positive. So Bn is a decreasing sequence with limit of Bn 0. Alright. So Bn is a decreasing sequence whose limit is 0, and hence by Dirichlet test this series summation a and bn is convergent. Alright. For all those x for which x is not an integral power of 2 pi. For which x is not integral multiple of 2 pi. Alright, and what happens when x is integral multiple of 2 pi? In that case, the series is simply summation 1 over n raised per p, because cos of nx would be 1. For all those x for which x is 2 or pi, cos nx would be 1. So, in that case, the series simply reduces to 1 over n raised per p, alright, which is convergent if p is greater than 1, and which is divergent if p is less than or equal to 1. So we have also discussed the case when x is equal to 2 or pi. In that case, the series is convergent for p greater than 1 and divergent for p less than or equal to 1. Okay, this is p series. And when x is not equal to 2 or pi, then the series, by Dirichlet test, the series summation a and bn is convergent. Alright, so I hope this is all clear to you. And now we, with all these theorem exercises, we come to the assignment that you have to do. So in this assignment, we have 5 questions. You have 5 questions which you have to attempt. So with this assignment is based on Abel's test and Dirichlet test, and all these exercises are based on Abel's and Dirichlet test. The first question in this assignment that you have to do is state and prove the Abel's test and Dirichlet test for the convergence of an arbitrary series. Alright. The first question is state and prove Abel's test and Dirichlet test for the convergence of an arbitrary series. Alright. The second question is discuss the convergence of the series summation an over n raised per p where p is positive if the series an is convergent. The third question is discuss the convergence of the series summation n varies from 1 to infinity. Alright. Minus 1 is per n sin nx over n raised to power p. This is question number 3. Question number 4 is show that the series summation minus 1 by 2 raised to the power n minus 1, n varies from 1 to infinity, into 1 over n is convergent. And the question number 5 is discuss the convergence of the series summation 1 over n varies from 1 to infinity, 1 plus 1 by 2 plus 1 by 3 plus 1 by n sine n theta plus alpha. Okay, you have to discuss the convergence of this series. So all these questions are based on Abel's test and Dirichlet test, and I hope you will be able to do them all. So that is the end of Abel's test and Dirichlet test in your course. We will be discussing uh, more results on series in the coming up video lectures. So I thank you all for attending all this lecture. Thank you.